Hello everyone, my name is In-Kwon Park, working in RTDS, and you can see my name under presenters in your attendee window. So if we want to ask questions and if we want to use my name, then you can see my name over there. Then yeah, thank you very much for joining us for this webinar. And then I know you are coming from all over the world, so probably it will be too much to say that good morning. But it's now in 10 a.m. here, so good morning, everyone, and thank you again for joining us this webinar. And the first thing I want to ask you to do is that there is a handout, so you can go down to the right bottom side of your window, then you will see a file, webinar handout.pdf. So please download that file and open up the file or print the file, then try to fill out the blanks in the file. So then I hope that would give you more chance to pay attention to the presentation part of this webinar. So this is the outline of the webinar, and we will start from the presentation part. This webinar would be composed with two sections or two parts. The first part is the presentation, and the second part is the demonstration. And during the first part, I'll try to do a little bit of explanations regarding the theory side of the power electronics simulation on the RTDS. Oh, sorry, I forgot to call the title of this webinar. The title is Power Electronics Modeling, Simulation, and Interfacing Controllers. Then the first topic under that first part of this webinar, the presentation, is what the real means and then what is the combination between real-time and simulations. Then we'll go to the second topic, which is the modeling of a switch. Probably most of people here are already familiar with the switch is the fundamental component of almost any power electronic system, so it's very important to have a good understanding regarding how a switch is modeled in your simulations. Then the third topic in this presentation is regarding the interface. And the interface is separated into the two portions. The first one is regarding the internal interface. Internal interface means the interface between the subsystems in your circuit or your simulation. Then we will go over into the second part, which is regarding the external interface. And external interface is for the I/O card between the RTDS and your external controllers. Then we'll have a look at the available models in RTDS Power Electronics Simulation Library, or what we call as a small time-step library. Then we'll go into the demonstration part. In the demonstration, I'll start from the standalone STATCOM case. Standalone means that everything would be included in the simulation case. The power stack is there and the control is there. Then the next part of the demonstration is the closed-loop testing of external control with RTDS. And the same STATCOM case will be used, but in the demonstration part, the control would be implemented on the external control, which is based on one of the Texas Instruments DSP. And still the power stack would be inside the RTDS. So that would be the second part of the demonstration. Before going into any serious part of the presentation, let me deliver the good news. At the end of each section or each segment of this webinar, there will be a quiz. And the winner of the quiz would be able to win one of these Texas Instrument Piccolo experimenters kits. Right now we have 5 of them, and this webinar is composed of the 5 sections, so we'll have a 5 chance to win the prize. So pay attention. Then another reason I just pointed, or I asked you to download the webinar handout, is that the quiz will be coming out from that handout. So you may want to pay more attention to fill out all those blanks in the handout. Not only for the kit itself, I tried to make it as a complete. And I put this pin headers in the box. This is a pin header. Then I also included this jumper wires. So I hope you would be able to create or recreate what will be done as a demonstration in this webinar on your desk with your own kit. But still, you need a tool like this, screwdrivers and wire clippers, of course. We need to use the tools to make the necessary connections and so on, and then you would be able to have a chance to look at what would be the necessary procedure to interconnect the Texas Instrument Piccolo Experimenter's Kit to the RTDS in later part of this webinar. So hopefully some of you would have that opportunity to give us the right answer on each of those 5 keys, then we'll be able to get one of these experimental kits as a prize. So this is the first topic in our presentation. It's regarding what that real-time means and then what is the combination between real-time plus simulation. So we'll talk about the concept of real-time first, then we'll talk about the size of a time step. In particular, the size of a time step becomes more important for the power electronics simulations. Then we'll talk about what would be the adequate size of that time step in terms of running the power electronics simulation. So real-time. It's very important concept, but at the same time, the word is very vague. Anyone can define the real-time in their own terms. So let me bring up a very simple example. Nowadays, Nintendo Pokemon Go game is very popular. So you are playing the game on your cell phone. And you've been playing the game for a while. Now you have a lot of Pokemons and the Pokeballs and then other gadgets in your room. And now you think that it's time to go to a gym, Pokemon gym, and try to reoccupy or repossess that gym. So now you are well prepared, and one of your Pokemon is now on the ring to fight with your own enemies. But suddenly something happened, and your cell phone screen stops, freeze, and even if you pound on the screen, nothing happens. Then your sense of being there in the middle of the game is lost. So that would be the meaning of real time when it comes to playing a game like a Pokemon Go. Then let me bring up more realistic example in terms of the real-time simulations. Let's assume that now you became one of these power system protection relays. You are now impersonating these relays. Then the input of the relay is the voltage signal and current signal from the real power system. As long as you sense those signals flowing smoothly and coming into your sensory input, such as a CT or a PT, it's fine. Now you are in the real system, and you don't have any doubt regarding the authenticity of the real power system. But once there is a small glitch or a small pause of the signal, then you can readily recognize that I'm not connected to the real power system. It's a fake. So that's the quality, and that's the definition of real-time in real-time power system simulations. It's very high quality, it's very delicate, and it's very difficult to maintain that true real-timeness in the real-time power system simulation. So until 5 or 6 years ago, the only high-power power electronics applications in the realm of real-time digital simulation is the LCC HVDC and SVC systems. Of course, nowadays, many people are talking about the STATCOM system, MMC HVDC, VAC HVDC, and microgrid, and all those renewable sources. But quite a while ago, or even like 5 or 6 years ago, not that many people thought of the possibility of bringing in all those newer power electronics application into the system. So in those old days, all those high power application of power electronics were based on the thyristor, or is still based on the thyristor. And in the thyristor-based system, the gating signal or firing pulse comes to the switching device only once per cycle. So the switching frequency of the system becomes the same as your fundamental frequency, either going with the 50 Hz or going with the 60 Hz. So the issue associated with such slow switching system is how to capture that exact moment when the firing pulse is coming into your simulation. In RTDS, we are using a technique named improved firing in order to capture that precise moment of the gating signal or firing pulse coming into the RTDS simulation. But in offline simulation world, one of the widely used technique is what people call as interpolation. In here, this is the simple diagram showing how that interpolation works. Let's assume that at this moment, at this red bar, the simulator, either your PSCAD software or any other offline software, receives the gating signal or firing pulse. Then the earliest moment when that simulation engine can detect that firing pulse is the beginning of the next time step, this moment. So unless we do any other processing or the precision detection method, there is a one time step uncertainty. When we are standing at this beginning of the time step, it's very difficult to tell when was the exact moment of the firing pulse. So in interpolation technique, in here, we move back to the moment to the exact firing pulse, and then the simulation engine move over one time step from here to here. Then it tries to come back to the original standpoint, which is the beginning of the next time step in here. So in this operation, we have two interpolations marked by this green arrow, the first one, then second one. So in here, and if you are running the offline simulations, then it doesn't matter whether this size of this arrow marked by this big question mark is either big or small. But what if that period marked by this question mark is very small? Then again, if you are running the offline simulation, it doesn't matter because the simulation or your simulator has the time of the world, so it can do whatever it wants to do before it finishes all the necessary business to do the precise detection of the firing pulse. But what if your simulation should run in real time? Then when you are standing at this point at the beginning of the next time step, everything already became history. That means it becomes very difficult to make the necessary correction in terms of the precision detection of the firing pulse if this period is very small. So the only option left for a real-time simulator or real-time requirement is that it should skip the time step and do the interpolation business at the next time step. And as a result, it should experience the extra delay in the time step. So that's the implication coming with the real-time restriction. So in offline simulation world, because it has a time of the world, it can do whatever it wants to do, and it can spend whatever amount is necessary to do the business. But in real-time world, because of the time step restriction or real-time restriction, it's very difficult to do or complete that operation when that available time becomes very small. So that's the practical limitations coming with the real-time requirement. Then now we can talk about the adequate size of the time step, especially for the power electronics simulations. Let's start from very simple given fact. Almost every power electronics simulation is composed of a semiconductor switch. And in order to ensure the full turning off of a switch, we need to give it the dead time. So let's assume that the size of necessary dead time is 2 microseconds. Of course, it depends on your application, your size of the system, or characteristic of the semiconductor switch, but just simply assume that we need a 2 microsecond delta time. And most of people here are familiar with the implication coming from the dead time. It's a disturbance. So we need to suppress the impact coming from that dead time. That means we need to have the sufficient amount of a switching period. If the dead time is a 15%, 50% of your switching period, then you have a very little room for the control. So usually we need to make it that dead time less than 1% of the PWM or switching period. Then automatically the switching period becomes 200 microseconds, or your switching frequency becomes 5 kilohertz. Then some literature says that the necessary size of a simulation time step for a power electronics simulation should be less than 5% of the fastest dynamics. Fastest dynamics usually means your switching frequency. So if the switching frequency is a 5 kilohertz or your switching period is a 200 microsecond, then the necessary time step size becomes a 10 microsecond. But in more conservative approach, or more power electronics engineer would feel comfortable with smaller time step. So usually the 1% becomes the criterion. Then the adequate size for your power electronics simulation should be around 2 microseconds. So this is the way how we can figure out the necessary size of a time step when it comes to running the power electronics simulations. So this is the end of the first segment, and now it's the time for the first quiz. And our quiz is, what percentage of a PWM period is regarded as a good simulation time step? I'll give you 2 minutes.
We have a winner already.
So still you have about 1 minute. So take your time to come up with the answer. So I believe many of you already came up with the right answer, and then there was a winner, and then that winner, I believe, already got the personal message saying that you won the prize. Congratulations. But still, we have many more chances throughout this webinar, so no worry. And then I wish you good luck for your chance to win one of those boxes. The next topic I want to talk about is the switch, how to model a switch in our simulations. And this is the flow of this part of the presentation. We'll start from the recap of the EMT algorithm. EMT stands for the electromagnetic transient. So we will refresh our knowledge regarding how the simulation goes in our simulator. Then we'll have a look at how a switch can be modeled under that EMT algorithm. So let's say we have a circuit like this, and we want to solve the circuit. Solving the circuit means we want to get the node voltage on every point of the node in the circuit, and we want to get the branch current in every branch in the circuit. Of course, if we have a paper and if we have a good capable calculator in our hands, then solving such a circuit is not a big deal. But what we want to do is that we want to ask a computer to solve this circuit. So in EMT algorithm, we can solve a circuit like the one in the previous slide in very systematic approach. So the very first step we may need to take is the model discretization. Model discretization means that many of the components, such as inductor and capacitors, can be described as a set of differential equations. Of course, once again, we have a paper and a good calculator, then we can solve the necessary differential equations by our own hand. And then even there is a chance to see that you can come up with the exact solution of those differential equations. But again, what we want to do in here is that we want to ask a computer to solve our circuit. So the model discretization means that we need to apply certain integration technique to translate or transfer those differential equations into the algebraic equations. So that's the first part of the EMT algorithm, and then I believe many of people here are already familiar with the usual integration technique under the EMT algorithm, which is a trapezoidal rule. So after applying that discretization, we can transform the circuit in the previous slide into the circuit like this. Now, instead of dealing the differential equations associated with the circuit elements, such as a capacitor or inductor or any other devices in your circuit, the only component left in the circuit is either the admittance or the current injection. Then we can build up the admittance matrix, usually called as a Dommel admittance matrix, like this one in this slide. Then we can build up the current injection vector, like this one. Then by doing these operations, G inverse multiplied by the current injection vector, we can get the node voltage. So this is the fundamental way of solving a circuit under the EMT technique. And this operation is usually called as a network solution. So again, very simply speaking, EMT algorithm is composed of two parts. The first one is the discretization of all those dynamic elements. Dynamic elements means that the elements can be described by the set of differential equations. Then the second part is the network solution, solving the circuit based on the G matrix and the current injection vector. So again, if we are running the necessary calculation in our offline simulations, we have a time of the world. So it doesn't matter whether the single time step solution can take an hour for the simulation time of 1 microsecond. So what we can do is that we run the simulation in our computer, then we can go back home and have a good time with our family, and then the next day morning when we come back to our office, the simulation result would be on your computer screen. So as long as we are not concerned with the real-time simulations, it's fine to have a huge amount of time for the simulation. But when it comes to real-time simulation, the story becomes different. Then again, our fundamental concern regarding the power electronic simulation is a switch. And how to model the switch is very important for not only for the offline simulators, but for the real-time simulation as well. What is a switch? We can simply think it as the combination between on-state and off-state. Of course, the on-state can be represented by the small amount of resistance or a small amount of inductance, the impedance. Then the off-state can be represented by the very high size resistor or higher amount of impedance. So very simply speaking, the switch has two states. on state and off state, and each state have its own impedance value. That means whenever that switch changes state, either from on to off or from off to on, the G matrix, which incorporates that switching element, should change. That also indicates that whenever such state change happens on a certain switch in your circuit, the G matrix has to be inverted again. Then we are all familiar with the price we need to pay for inverting the G matrix. It comes with a substantial amount of calculation, so it takes time on your processor. Again, if your simulation is operand simulation, it doesn't matter. But if you need to run the simulation in real time with a very small time step, then it matters. So there are alternative approaches. Matrix inversion is very expensive in terms of the amount of the calculation. So usually what we do is a matrix decomposition, such as a QR factorization, LU decomposition, or Cholesky decomposition. But still, the decomposition is composed of many calculation steps. That means it's not simple or easy to finish up that calculation with very short period of time on your processor. So then we need to find a way to reflect the change of state of a switch in our simulations with minimum amount of extra calculation, or the calculation associated with the switching state change. So in RTDS, the fundamental approach is what people call as a small L, small c switching. The on state of the switch can be represented by the inductance, or the small L. Then off state of a switch can be represented by a small capacitance, or C. Intuitively, it makes sense to us because on state is a short circuit, and we can consider the inductor as a short circuit. Then off state is open circuit, and we can consider the capacitor as an open circuit. So by carefully selecting that L value and C value in the switching technique, small L, small c switching, we can make the domain admittance of those circuit elements the same. That means we can fix the G matrix, and we can pre-invert that constant G matrix before the starting of your real-time simulations. Then we can avoid the inversion or the refactorization of admittance matrix on the fly. So we can save the calculation time. And that's fundamental way in RTDS in order to ensure the size of a time step is small, and we can maintain that small time steps throughout our simulation. But there is no free lunch, and that the method comes with its own side effect. All of us know that combination between the L and C is not equal to the real ideal switch. One of the side effects coming from that approach is that there is a time step size restriction. Many people consider that about 1 million time between on impedance and off impedance is necessary to depict the true behavior of a switch. And as you can see from this graph, that 1 million time boundary is around in here. This is 1 million, then around in here is the time step boundary. So we need to ensure that the size of a time step for our simulation would be less than this criteria. So this point is around the 2.5 microseconds. So we need to make sure that our simulation runs in the smaller time step size than 2.5 or 3 microseconds at most. Then another side effect is the fictitious loss. I believe all of us are already familiar with this formula. The inductor is an energy storage device, and also the capacitor is an energy storage device. Inductor stores the energy in the form of the magnetic field, and the capacitor stores the energy in the form of the electric field. But in real life, the switch is a switch, not the energy storage device. So this is purely fictitious, only happening in your simulation. So as long as your switching frequency is low, then probably you can go with the fact that your circuit comes with a little bit amount of fictitious load, but then if you raise up your switching frequency, then the value, the fictitious loss, would begin to show up in your simulation result. So that technique has been in RTDS for a very long time, and we've been aware of those side effects coming from the approach. So the model like this is also included in RTDS small time sum library. This is what we call as a low loss bridge model. Then this model is based on the true switching. True switching means that a switch inside of this model, two-level bridge, is modeled as a combination between R on, R off, or low impedance for the on state and then high impedance for the off state. So it doesn't incur that fictitious loss. So now it's the time for the second quiz. And the quiz is, what is the word in this blank? Discretization transforms what equations to algebraic equations? This is your quiz. So I'll give you 2 minutes. So now it's time to move over into our next topic, which is regarding the interface. We already picked the winner, or the winner was identified, so I don't see too much point of waiting the full 2 minutes. So I just decided to move over into the next topic in order to spend more time on the more interesting part of this webinar, which is the demonstration. So the topic I want to talk about is the interface. Interface can be separated into 2 categories. The first one is the internal interface between the simulations, and the second one is external interface between the real-time digital simulator and the external device. So you have a circuit like this, very big circuit. Let's assume that this is your 100 bus AC system simulation case. And all of us are familiar with the technique to separate the big circuit into the multiple server circuit. And the way is by using a transmission line model. And the requirement of the line model is that it should be longer than your simulation size. So in mathematical terms, by applying the technique, we can make the entire 1G matrix into the several smaller G matrices. Then the calculation time would be less than dealing with this big one single G matrix. And in RTDS terms, that separation, or making the subsystem, allow us to put each of those sub-circuits on a different rack in RTDS. So we can still maintain the real timeliness of your simulation while the simulation size grow bigger. So your 100 bus system, AC system, can run on the 2-rack RTDS without too much difficulties. And again, the way of separating the circuit is by using this transmission line interface. Then the similar issue is there between the large time step circuit and your power electronics simulations. Many times, you want to just leave the conventional AC circuit in the large time step domain because there is no particular reason to bring everything into your small time step simulation or your power electron simulation. But meanwhile, you want to preserve that high resolution of the simulation in the small time step. Then the way of bridging those two different worlds together is by using the transmission line model. In this case, I believe many people here are familiar with all those existing models in the RTDS small time step library. Sometimes we use the interface transformer and sometimes we use the interface transmission lines, but the underlying algorithm behind either interface transformer or interface transmission line is all the transmission line, and the length of a transmission line is 1.59 large time step. That means inductance can be covered by either the L value of the transmission line or leakage value of the transformer, but still the associated C is there because the travel time of a transmission line is a square root LC. And we need to ensure that that size of a large time step, which is 1.59 large time step, has to be covered by that square root LC. And the same issue arises when you are dealing with a quite substantial size of the small time step network. In here, what we are looking at is the big power electronics circuit. Then you can separate that big power electronics circuit into the several sub-circuits by using the shorter transmission line. Because in small time step simulation or in your power electronics simulation, the size of a time step should be very small in comparison with the size of a large time step. That means the necessary length of that transmission line should be much shorter than what you would use in your large time step. And by using this technique, you can distribute all or those several sub-circuits into the several processors available in your real-time simulation hardware like this rack. Then that's not only point where you would find the transmission line. In a single circuit like this, still we will find the small time step transmission line models. In here, the two-level bridge is represented by the low-loss bridge model, or in other words, this part of the circuit is represented by the true G matrix switching. Then the rest of the circuit is still based on the conventional way of modeling, which is the constant G matrix approach. Then we have all these transmission lines at the boundary in order to make sure that the stability of entire simulation, stability means numerical stability, can be maintained. So all these transmission lines are acting as an interface between the G matrix inversion network and the constant G matrix approach-based network. And of course, you don't need to place all these individual transmission lines in your simulation. These line models are part of that low-loss bridge model, so we don't need to take a big concerns regarding the line models, but still it's good to have this point in your mind when you are designing the circuit or your simulation case. Then now we are turning into the physical interface or the external interface between RTDS and your external control. In regards to the analog interface, we have a GTAI card at the left side. Very simply speaking, GTAI card can be considered as your AD converter. So it converts the analog voltage value at the terminal into a numerical value, which to be reflected in your simulation. And this GTAI card has 12 channels, as you can see in here. Then the resolution of each channel is a 16-bit. And at the right side, we have a GTAO card. Very simply speaking, this GTAO card can be considered as your D2A converter. So again, the total number of channels in this card is 12, and each channel has a D2A resolution of 16-bit. So now we are looking at the digital interface. At the left side, we are now watching the GTDI card, which is the digital input to the RTDS. Digital means that the nature of the signal is either off or on. And this card is to be used as a way of bringing your gating signal into the RTDS. We will see how we can interface the external controller to this card later on. Then at the right side, we have a GTDO card, which exports the simulation value as a digital signal to the external control. And not only for those physical signal interface, now it's becoming more and more important to have a communication interface. And then RTDS offers this interface card named the GTNet X2 in order to lay down the bridge between your simulation and external world through the communication. Very simply speaking, this card can be considered as your network interface card in your computer. Then now more and more applications are regarding the high precision in the time synchronization, and the typical example of such requirement is the PMU or synchrophasor applications. So in order to accommodate such requirement, RTDS offers this interface card named the GT Sync card. This card can bring in the external high precision clock reference such as a GPS into the RTDS, and then this card can regulate the internal clock of RTDS in order to match that clock with that high precision external clock reference. Then we can run the RTDS side by side with the real system because clock is matched with the precisely matched with the real world clock. And then now the power electronics applications are becoming more and more complex, and then more and more signal have to be interfaced between your simulation and your external control. In such case, the only way of transferring large amount of data is by using the high-speed fiber optic communications. And this interface, based on the MMC support unit, can accommodate such requirement. This interface is what we usually call as a GT-FPGA, and then we offer the net list, which represent the fiber optic connections between the RTDS and the MMC support unit. Then from there, you can establish your own interface, and then you can connect the optical connection between this box and your external controller. By doing that, you can exchange large amount of information between RTDS simulation and your own control. So now this is another moment or another opportunity to win a prize. Then the quiz is, how many channels does a GTDI card have? Congratulations. Now we identify the winner, and the winner will get one of those boxes. Congratulations again. So again, we don't need to spend too much time because we already identified the winner, so I can move over into the next topic, which is regarding the available models in RTDS Power Electronics Simulation Library. We'll have a look at those existing models first, then we can move over into the more recent development in terms of the power electronics simulation in RTDS. The fundamental component of your power electronics simulation is a switch. So RTDS library, you can find many different switching models, but you need to keep the point in mind. All these apparently looking different switching models are all based on the same approach. The small L, small c switching, and the switch itself is I would say, the ideal switch. Then we have aggregated switch model, such as this aggregated 2-level bridge model or this 3-level MPC ARM model. The benefit of using this aggregated switching model is that because the topology is already known, RTDS can optimize the amount of calculation to be used for your simulation. That means we can save the necessary simulation time when it comes to running the real-time power electronics simulations with all these switching models. By using this bridge model, you can model the 2-level bridge, and by combining 3 of these, you can build a 3-phase, 3-level MPC bridge. Then again, we can save time in our real-time simulations. Then RTDS Small Timestamp Library, or Power Electronics Simulation Library, includes the machine models. This is a three-phase synchronous machine model. This is a three-phase induction machine model, and this is a three-phase permanent magnet synchronous machine model. One of the benefits of this three-phase synchronous machine model is that it can be interfaced with the existing generator controller models in RTDS large timestamp libraries, such as governor, exciters, so you can incorporate the characteristic of those generator control models while running your machine in small timestamp. And regarding this induction machine model, we can model the rotor side of circuit as a squirrel cage or to be exposed into the external circuit through the interface. Then you can model this machine as a DFIG machine, doubly fed induction generator machine. Then we have many different transformer configuration in the small timestamp library, and we have a separate saturation branch model in the small timestamp library. That means you can do almost exactly same simulation as you would do in large timestamp by using some of this transformer model in your small timestamp or in your power electronics simulation. Then RTDS offers all these fundamental control blocks in the small timestamp library. The reason why we have all these very basic control blocks in the small timestamp library is that many times you may want to manipulate your gating signal. So certain bit has to be in certain position, but somehow the input to your control is not properly arranged or aligned. Then by using some of these control blocks, you can create the necessary gating signal pattern, or you can shift a certain bit from one position to the other. So that's the reason why we have all these control blocks in the small timestamp library. Then now practically all of the high power power electronics applications are now converging into a same or single topology, which is usually mentioned as a MMC, multi-level modular converter. So RTDS offers 3 different ways of modeling MMC system in your simulation case. The first one is what we call as MMC5. MMC5 is based on the average model approach. So each individual capacitor in your MMC arm would be represented by one single capacitor, so that the model can be considered as average approach for the MMC modeling. Then the second model RTDS can offer is what we usually call as a chain B5 model, and that chain B5 model is based on the processor, so you don't need to have any extra hardware in order to run the simulations. But then the third category of existing RTDS MMC model is based on the FPGA, and then what we usually call that FPGA model as a MMC FPGA model. So you have a freedom to choose the most suitable model into your simulation. If you are more concerned with the AC system dynamics, then you may want to go with the average approach model, which is MMC5, or if the level or the number of submodules in your arm is small, then you may want to go with the processor-based MMC model, which is chain B5. But if you are concerned more with a large amount of submodule in your system, then probably you need to go with the FPGA MMC models. Then this is a DC breaker model in RTDS library. Probably many people here are working on the microgrid or DC grid, and one of the key components in the DC grid or microgrid is the DC circuit breaker. In AC circuit breaker, it's relatively easy to cut the current. In AC fundamental cycle, there is one zero crossing, and we know that once we open the contact of a circuit breaker, that zero crossing will ensure that current will be interrupted by opening up of the contact. But in DC system, there is no such thing as a zero crossing. So we need to create the current chopping or current interruption capability by using a specific topology. And this is one of the ways. And in here, we have a 2 conduction paths. The upper path is the usual conduction path, and lower path is composed of serially connected arresters. So Once the command comes in to open the circuit, then we can open up the regular conduction path, and the current will be commutated over into the series connected arrestor conduction path. Then those arrestor would be able to build the necessary back voltage in order to interrupt the current. And that's how this, what people usually call as hybrid circuit breaker, DC circuit breaker, works. And we have this DC circuit breaker as a model in small timestamp library. And then this is a single-phase circuit breaker model. As you already noticed while we are talking about the switching model, because the switch is based on small L, small c switching, even if the switch is in off state, it's not fully off. For example, if your system frequency is 400 Hertz, then even if your switch is open, it's still capacitor. That means it will flow the current because the system frequency is AC. So we've been aware of that the characteristic of LC switching, and the left side we have a single phase real circuit breaker model with a pre-insertion register. So real circuit breaker means that it's a R on R off type approach based circuit breaker. So we can make our power electron simulation closer to the real life system by using this model. And the right side, this is the real G value switching model without this half time step interface lines. So this circuit breaker or the switch model can directly participate in the G matrix manipulation business. So then we have this arrestor model in the library. So we can create the power electron circuit with the proper representation of arrestor. Then we have this more complex or more realistic FPGA-based MMC model. And this model is what we usually call as a GM model. And by using this model, we can create a more or rich set of fault scenarios. And then we can use this model for the more realistic testing of your external MMC controllers. And the last topic I want to talk about in this segment is the subsystem model. Subsystem means that the model like this runs multiple time steps inside a single regular small time step. For example, as you can see here, this model runs 4 times in a single small time step. So let's say your size of a small time step is 2 microseconds, then this model would run on its own time step of 500 nanoseconds, which is quite comparable to the dedicated FPGA simulation platform in the market. So for example, we can achieve such a small time step as a 588 nanosecond by using this substep 2-level bridge model. And this 2-level bridge model is based on the true switching. That means we don't need to worry about the fictitious loss coming in the small L, small c switching technique. The benefit of having such a small time step is that it allows us to capture very short time frame event, such as a true dead time. As you can see from this scope screen, the size of dead time is 1 microsecond, 2 squares in this scope. Then we can capture that dead time event in our subsystem model like this. So by using the subsystem model, we can capture very short duration time event in our simulation. Then this is a substep 3-level bridge model. The bridge model itself is still based on small L, small c switching, but because the size of a time step is much smaller than the regular small time step, we can expect a smaller loss coming from the model. And then now it's the time for the quiz again. And the quiz is, what does MMC stand for? So now we have a winner. So I can move over into the next topic, which is the demonstration of this webinar. Before going into the demonstration, I want to point one more preparation you need to do in order to create the same circuit as I have on my desk, which is the common terminal block for the GTDI card ground. And then I believe you have a soldering iron and the solders and a small piece of wires. Then by using the pin header and your wire clipper, you can create the small piece of common ground like this. Then you can take out one of those terminals from your GTDI card ground side. Then you can put this pin header with a common ground connection into it. Then we will have a common ground at the ground side of the GTDI card. It will make things much easier in terms of making the connection. So this is one extra preparation in order to create the same circuit as I have in my desk for the demonstration. So the first part of the demonstration is the stand-alone simulation case. And let's have a look at the simulation case. So here is the standalone simulation case representing a simple STATCOM system. We have an AC side circuit which represents your AC system, and then I believe many people here are familiar with the technique of representing the AC system strength by using the certain combination of R and L. So in here we set the impedance of a three-phase source to represent the system strength of 667 MVA. Then next to that three-phase source, we have a fault model. We have a line-to-line fault and line-to-ground fault, so we can simulate the behavior of a STATCOM system when we apply the fault, such as a line-to-line or line-to-ground. And we have a circuit breaker in here. Then let's have a look at our small time step simulation. Here we have an interface between the large time step and small time step. And here we have a load. The size of a load is 100 MVA, and the power factor of the load is 0.6. So whenever we put in this load into the system, the load will consume the reactive power, which is supposed to be compensated by our STATCOM system in here. Or if we do the other way around, we cut off the load from the system, then this STATCOM needs to reduce the amount of Q production in order to maintain the AC side voltage. And here is a filter, and here is a 3 transformer representing the transformer between the 2-level bridge and the rest of the system. Then, as usual, the way of making the connection in this transformer is Y delta. And in here, we have a 2-level bridge. And by controlling this 2-level bridge, we can adjust the exchange, the Q exchange between the bridge itself and the rest of the power system. And that's the mechanism behind the STATCOM. Then in here, we have a control. Control is quite simple. We have a PLL in here, and then PLL is supposed to detect the AC side phase, and that phase will become the input to our ABC to DQ transform and DQ to ABC transform in here. And we can read the phase current, and we can do the proper scaling here in order to make the control based on the per unit basis. Then we do the ABC to DQ transform in here in order to make the D-axis current and the Q-axis current. Then the D-axis control or D-axis current control is responsible for adjusting or regulating the real power, while the Q-axis control is responsible for adjusting the reactive power. So higher level of D-axis control is a DC voltage control, as you can see in here. Then the higher level of Q-axis control or reactive power is regarding the regulation of the AC side voltage, as we can see in here. And the control concept behind of this control is what you are already familiar with, the DQ decoupled control. Decoupled means that we have a cross-coupling due to the transformer, the leakage reactance, and then these two terms are representing that decoupling terms. So the next thing we want to have a look at is the actual simulation by opening my runtime. Here is a simulation, and I believe most of people here are familiar with the capability inside our runtime that we can draw the one-line circuit like this. Then that will make the entire simulations more appealing. Your boss would be able to understand what's going on. Unless you have a circuit like this, it would be quite difficult to figure out what's actually going on in your circuit. So let me start the simulation case. So now the case is running, and seems like everything is well simulated. So the first thing I want to give it a try is that the AC voltage regulation. Let me change this reference from 1.0 pu to the 1.05 pu like this. Then almost immediately we can notice that this AC voltage measurement is very close to the reference, which means the Q-axis control of our STATCOM system is working as expected. Then let me change this DC reference from 1.6 pu to the 1.8 pu. So now the DC measurement in kV kilovolt term, not in pu term, is higher. That means probably this reference is very close to this measurement. Is very close to this measurement. Then the next thing I want to give it a try is that to see what happens if I cut off the load from the circuit. So I turn off this switch. Then this is the Q production curve from the STATCOM system. Because load is now disconnected, the STATCOM needs to reduce the Q production. And this curve clearly shows that it was at this level, very high level of Q production. Then once the load is cut from the system, the Q just goes down like this. And at the same time, this is a branch current. When the Q production is high, the branch current is also very high. But then once the circuit or that load is disconnected, then we can see that the branch current goes down as well. And we can do the other way around by turning on this switch. So then now the Q production goes high again in order to compensate that extra load coming into the system. And at the same time, we can see that the branch current becomes quite high. So this is the very simple demonstration of a standalone STATCOM system. And after this webinar, you will be able to get all the necessary files for this simulation case. Then the next demonstration I want to share with you is the real closed loop testing of Texas Instrument DSP and RTDS. The simulation case would be the same as this standalone STATCOM case. The simulation case would be regarding the operation of a STATCOM, but instead of having everything in your simulation case, the control part would be implemented on a DSP, and we will see how we interconnect that DSP-based control with the RTDS through the GTAO card and the GTDI card. So that's me, Inquan, and then we have that Piccolo experimental kit. Then what I'm doing over there is I'm now opening the box, and the box is mostly the styrofoam. So even if the box looks very big, what's inside is not that many. So I'm taking out the control card, so you may want to pay a little bit extra attention to find out the card, because the card is fit into the slot like this at the right side of the box. And what I'm doing over there is that taking out the USB cable. Then that's the baseboard. So that's the contents of the box, and then I'm now closing the box. So now I have everything on my desk, and then taking out the baseboard. Then I'm now taking out the control card, which is based on the Texas Instrument DSP named the TMS320F28069. And it's very easy to put the card into the baseboard, and then so this is what it looks like when you put the card into the baseboard. We have 2 latches, so make sure that you put these latches into the position once you place the card in the slot. And we have these pinouts at the both sides of the card. Then that's where we would make the jumper wire connection between this board and the I/O card of the RTDS. And this baseboard comes with a little bit of a breadboard area, so if it becomes necessary, you can build up your own circuit. Then we have this USB connector in here, and we have this toggle switch. And what I'm trying to do is that I want to make the USB connections between the board and my laptop computer. And this is the USB isolator. So in order to protect your laptop computer from the controller, I would recommend to use the isolator like this. Of course, even without this isolator, you can make the connection between your laptop computer and the controller. But just in case, if something happens at your controller, without the isolator like this, you will, or your laptop computer will get damaged. So in order to prevent such accident, I would recommend to use the isolator like this. But again, you can still continue on your experiment without the isolator like this. So this is how it goes. And then once I turn on the power, which is provided by my laptop computer, you would be able to, or I would be able to see that all these 3 LEDs are turning on. Then what I'm doing here is that by using the jumper wires, I'm making the connections between the board and the I/O card. And this is how it looks like after completing all these jumper wire connections. I intentionally use the different jumper wire colors. So the orange color wires are representing the analog interface between the GT/I/O card and this control board. And the yellow color wires are representing the digital interface between this control card or control board and the RTDS. And of course, the simulation values would be sent from the GT/I/O card to the controller. And if you look at the controller baseboard, there are 8 pins of analog input and this side, and the connections are made between the GT/I/O card channels and those pins. Then these yellow wires are carrying the final gating signal from your DSP controllers into the RTDS. So the GTDI card would bring in the gating signal from your controller to the RTDS and drive the 2-level bridge. So we have a little bit of overrun in the time, so I can skip a little bit of this less interesting part of my preparation. So now my analog connection is almost complete, and then I'm almost come to the completion of making the digital connections. So as you can see from here, what I'm working on is not difficult at all. The only thing you need to do is by using your jumper wire, making the connections between the analog output of the RTDS and the digital input of your RTDS. So again, this is the entire setup. The yellow wires are carrying your gating signal from your controller, and these orange wires are carrying the analog signals coming up from RTDS into your control. And of course, you have these USB connections between your controller and the PC, and the PC will provide the power to your USB board. As you are already familiar with, the USB port power spec is 5 volt and 500 milliamps. So total amount of power you can get from the USB port is about 2.5 watts. But because this DSP is not consuming too much power, the USB power supply is sufficient to run this board. So no worry about having the external power supply for the controller. So now everything is ready. So what I'm doing over there is that I'll try to export the simulation values throughout the front panel of the RTDS. So we see that I have this pin, and this location will produce the node voltage from our simulation. Then I'm connecting the power to the scope, and then as we can see over there, around my neck, I have 2 probes. One probe will go into that front panel analog output of the RTDS in here. Then the other probe will go into the first channel of the GTDI. And that channel is representing the gating signal coming into the number 1 valve of a 2-level bridge, low-loss 2-level bridge. And that number 1 valve is upper side valve of A-phase arm in your STATCOM or 2-level bridge. So when that valve turns on, the node voltage in front of that A-phase arm becomes the plus DC rail voltage. Or in the other way around, when the switch goes off, then the bottom valve will turn on, then that valve will connect the minus DC rail voltage into the node voltage. So this is how does it look like at the RTDS side. I have 2 pins. One is a signal pin, and the other one is a ground pin. And you can make the connection between RTDS and your scope like this. So now the scope is turning on. Then again, now we are coming back to the simulation case. And this case is a little bit different from the STATCOM simulation case, as we have looked at previously. In here, we don't have any control. This case only has the power stack. All these control models are only for signal conditioning. And we have a similar, or the same power stack as before, but now we don't have any internal control. The only model inside this power stack is this real-time scope model, which allow us to have small time step simulation value observation from our RTDS RSCAD runtime. And here, as I explained, here are all the signal conditioning control blocks. The input voltage range of your DSP or the Texas Instrument DSP is from 0 volt to the VCC. VCC is usually 3.3 volt. And the kit doesn't have any extra signal conditioning circuit. That means by using the signal conditioning, we need to make sure that the signal coming from RTDS is in the same range as required by the AD converter. That's the reason why we have a signal conditioning circuit as a part of our simulation case. And now I'm starting the simulation case, but because no control is working, what we would expect from this simulation case is a natural response of a diode bridge. And here we don't see any gating signal. That means control is not started yet. And this is the Code Composer Studio, which is a programming environment of our DSP. And I have this software project named the two-level STATCOM, and then I wrote all this control code in order to make sure that this control code is the same as what we've seen in the standalone STATCOM case. And now I'm starting the control code. So the perspective of Code Control Studio is changing from the edit perspective into the debugging perspective, and then now the code is being downloaded into the DSP. And by click this button, the arrow button, I can start the control. But one more extra step I implemented in this code is that there is this flag PI_RST. So by changing this value from 1 to 0, now I'm enabling all the control in my control. And because I choose to use this constant update button, all those watch variables are now changing in real time. And this is how it looks like when the controller is working. You notice that LED is blinking in here, and this is what is like on the scope screen. This is the gating signal coming into the number 1 valve in RTDS simulation, and this is the corresponding node voltage change. As I explained here, number 1 valve represents the top side valve in the A-phase arm of the two-level bridge. So once the gating signal comes in, the switch turns on, then that will bring up the node voltage from the minus DC rail to plus DC rail. And what we can notice is that there is a certain amount of delay. The 1 square represents 5 microseconds, so the smallest delay we would see from the experiment like this is around the 5 microseconds. Then this is what it's like when you look at the entire experiment from the RTDS side. We have AC voltage measurement in here, then which is very close to reference. Reference is 1.0 pu. Then we have a DC reference here, and DC measurement here, and the DC reference value for is about 1.8 pu. Then we can see that the measurement is very close to the reference. And once we update here, it's a little bit small, but we can see that AC reference in here, then DC reference in here. So by changing the DC reference from 1.8 to 1.6 pu, we are expecting to see the corresponding change from RTDS simulation. And as you can see from this measurement, now this measurement is very close to the new reference, which is a 1.6 pu. Then once again, we try to change the AC voltage reference from the 1.0 pu to the 1.05 pu. Then, as you can notice from this meter, the AC voltage reading is very close to the new reference, which is 1.05 pu. And we do the same before. We just put in the load to see how the entire system reacts. And as you can notice from this Q production curve, the Q production goes from the low value to the high value. Then at the same time, the branch current is increasing because the STATCOM is now producing higher amount of reactive power. Then if I turn off the load, we see the opposite phenomenon. The Q production goes from higher value to the lower value. Then the branch current goes from the larger amount to the smaller amount. Then the very last item in this demonstration is changing the reference through the communications. I'm now checking the comfort status in my own computer by looking at this device manager. So now I have a USB serial port COM8, and I'll try to use that as a communication interface from my computer to change the reference on my DSP. In here, now we see one of the important jumpers on your control. In order to get that communication working, we need to insert this jumper at the location of J9. You can easily tell the location from this photo, or if you look at the control board, it's very easy to tell. So you may want to insert the jumper like this, or you can use the jumper wire in order to make the short connection on this jumper, and that will enable the SCI communication between your DSP and this FTDI chip. FTDI chip is responsible for handling the USB connections, and it provides the two logical channels coming out from the one USB connections. So one channel is being used for the controlling of the DSP itself, and the other channel is made available as a COM port or RSCI communication interface between the DSP and your host computer. So this is an expanded view, so you can tell the location of a J9 jumper in here. So then I wrote a very simple MATLAB MFile script in order to change that the Q or the BDC reference from the MATLAB onto the DSP by using the SCI or RS232C type serial communications. Now I'm changing the reference from the 1.6 PU to the 1.8 PU. Then once I run that MATLAB M script from my MATLAB command line, you see that the change has applied into this new DC reference value. And as you can see here, the DC measurement is coming very close to the new reference, which is a 1.8 PU. I hope you can apply the similar technique in your experiment, like your microgrid management system. So this is the end of the live demonstration, and let's go back to our favorite part of this webinar, which is a quiz game. So this is the very last quiz. So this is the only opportunity for you to win the prize, and the quiz is this. You are so quick. So I believe the winner is already identified. So let me have the opportunity to wrap up this morning's webinar. So first of all, I really appreciate your attention for more than an hour, and it took a little bit more than what we expected, and I'm really sorry for taking more time than expected. But again, thank you very much. So in this morning, what we looked at is like this. We started from the fundamental theory of the power electron simulation inside RTDS. We started from the real-time simulation, and we had a look at the example of a Pokemon game, Pokemon Go games. Then we moved over into the next topic of the simulation regarding EMT theory, very brief recap. Then we had a look at the way of modeling a switch in RTDS. Then we move over into the next topic in our presentation regarding the interface. We looked at how to interface the circuits inside our simulation, what I called as internal interface. Then we had a look at the external interface, which is regarding the I/O card in RTDS. Then we had a look at all those available models in RTDS small time set simulation library. Then we had a look at the couple of recent development, the DC circuit breakers and the MMC models and the subsystem model, the 2-level subsystem models and 3-level subsystem models. Then we move over into the later part of this webinar, which is regarding the demonstration. We had to look at the standalone STATCOM case first, then we went into the second part of demonstration, which was regarding the closed-loop testing of your external controller and RTDS. Again, thank you very much, and again, I wish you can apply the knowledge you've learned from this webinar in your research or your work. So now it's the Q&A time. Excuse me. The question from one of the audience is, what is the maximum PWM frequency to apply directly to the GTDI card in order to switch the low-loss 2-level BSC switches? So because we are talking about the low-loss bridge model, probably you don't need to be concerned with the artificial or fictitious loss associated with the higher switching frequency, but still the fundamental fact is there. What I mean as a fundamental fact is that the size of a small time step is there. As I explained in the first part of this presentation, the size has to be around probably 1% of your PWM frequency. That means, let's say your small time step is 1 microsecond. Then probably the maximum PWM frequency you can get is around 10 kilohertz. 10 kilohertz, the switching period is 100 microseconds, so 1% of 100 microseconds becomes 1 microsecond. So that would be the guideline in terms of picking up your switching frequency, in terms of interfacing your controller with RTDS. Of course, you can go with a higher switching frequency. There is no written rule or law which prevents the using the higher switching frequency. Then the implication coming from using the higher switching frequency in your controller is that now the impact of size of a small time step would become more visible in your simulation result. I hope this would have been sufficient as an answer for the question. Again, the question was, what is the maximum PWM frequency to apply directly to the GTDI card in order to switch the low-loss 2-level BSC switches? So then, even after this webinar, probably we can continue our discussion either by the telephone call or by the email exchange, or perhaps there might be a chance to see face-to-face if there is such an opportunity. So again, I wish everyone attending this webinar would be able to utilize the knowledge you learned from presentation and demonstration directly onto your research and your work. And please stay tuned with the further development from our company. Again, thank you very much for your attention and have a great day. Bye-bye.
The conference is now finished. You will now be disconnected.